We all think of chaos as, well, just pure unpredictable randomness. But what if I told you that hidden deep inside the most complex, chaotic systems, there's an infinite landscape of perfect repeating patterns? A brand new paper suggests there is, and honestly, it could completely change how we look at the universe. And that's really the big question here, isn't it? This research challenges everything we assume about chaos. It suggests that even in systems with 3 or more dimensions, where things get wildly complex, there might be these hidden rules, a secret order just sitting there waiting for us to find it. So here's our game plan for this explainer. First, we're going to hunt for some order where it seems totally impossible. Then we'll get into why adding more dimensions is such a huge problem. We'll uncover this really special chaotic pathway that kind of acts like a secret map, which leads us to the paper's huge discovery, infinite stable circles. After that, we'll look at the elegant trick that proved the whole thing, and finally, we'll talk about why this is such a big deal, way beyond just mathematics. Okay, so how in the world do you find a pattern inside a hurricane? Well, mathematicians who study chaos, they're not just watching the storm. They're looking for the calm eye at its center. They are hunting for predictability, for these stable endpoints that a system is naturally drawn to, no matter how crazy its journey is to get there. And that destination, it has a name. It's called an attractor. Picture this. You drop a leaf into a swirling river. It's going to take some wild, unpredictable path, right? But eventually, it's probably going to end up in a calm little eddy somewhere. That eddy, that's the attractor. It's the predictable, long-term behavior that's hidden inside all that short-term chaos. The real challenge, though, is finding these things in really complex systems. And that right there brings us to the core problem this paper is all about. See, moving from a simple 2D model to the 3+ dimensions of the real world, that isn't just a small step up in difficulty. No, it's more like graduating from reading a flat map to trying to navigate an entire galaxy. In 2 dimensions, chaos is actually pretty well behaved. It's like using that flat map. But the moment you jump into 3 or more dimensions, the complexity just explodes. There's even a name for it, the Newhouse phenomenon, where finding any kind of stable pattern becomes almost impossible. And this is the wild frontier this paper is exploring. So, how did the author manage to navigate this chaotic galaxy? Well, they did it by finding a very, very specific geometric pathway through all the noise. It's called a heteroclinic cycle, and you can think of it as a kind of secret map that points to where all the order is hiding. Okay, I know this diagram looks super technical because it is. It's straight from the paper. But let's just focus on the core idea, okay? A heteroclinic cycle is basically like a hidden roller coaster track inside a chaotic system. It connects 2 different unstable points, and it creates this looping pathway. Think of it as this really delicate bridge between 2 super precarious states. The system gets pulled towards this path, and it's right around the special track that something amazing begins to happen. Now, this pathway is picky. It doesn't just show up anywhere. It needs 4 very specific Goldilocks conditions to even exist. You need 2 particular kinds of unstable points. You need this delicate balance where one point is pulling the system in while the other is pushing it out. And, this is crucial, the connections between them have to be just right. One has to be a perfect direct hit, while the other is an incredibly precise near miss. It's a really rare and beautiful setup. And when you get all of those rare conditions lined up perfectly, that's when something truly incredible happens. This right here is the monumental breakthrough of the paper. So you've done it. You've found this incredibly rare pathway, this perfectly balanced cycle smack in the middle of all this higher dimensional chaos. What's the payoff? What does it guarantee you'll find? The answer is right here, in the paper's main theorem. Okay, I'm going to throw some jargon at you, but stick with me. Diffeomorphisms are just smooth, reversible transformations, and normally hyperbolic periodic circles are just a type of stable, circular pattern. Don't worry about the words. The core idea here is a stunning guarantee about what you're about to find nearby. Let me translate that for you. It means that if you find just one of these special pathways, the system is mathematically forced to create an infinite number of stable, repeating, circular patterns right next to it. It's not a maybe, it's not a possibility, it is a certainty. Hidden inside all that chaos, you are absolutely guaranteed to find infinite order. So how on earth do you prove something that profound? Well, the how is just as elegant as the discovery itself. Turns out the author used this really clever mathematical technique to show that all this complex behavior is secretly being controlled by a much simpler, well-understood system. This technique is called rescaling. Here's the game plan. You take your super complex system, you find that special cycle we talked about, and then you use a kind of mathematical microscope to zoom way in on what's happening right next to it. And as you keep zooming in, all that overwhelming complexity, it just starts to fade away, and a familiar, much simpler pattern starts to emerge. And this is the big aha moment. After all that zooming, the super complex behavior happening near our cycle on the left starts to look exactly like a famous, well-understood, chaotic system on the right called the Henon map. It's like realizing a scary, complex monster was just a simple shadow puppet the whole time. By proving these two were basically the same, the author showed that all the known patterns from the simple map had to exist in the complex one too. A problem that seemed impossibly hard was suddenly solved. And you know, the crazy part is that this whole elegant simplification was only possible because the author found and corrected a small but really crucial detail in an existing mathematical formula. It's just a beautiful reminder that in math, getting the tiniest details exactly right can unlock massive, massive new insights. Okay, so let's zoom back out. We've found a way to uncover infinite order in some seriously complex chaos. Why does this discovery matter for anyone outside of pure mathematics? Well, the impact here is huge. This work takes our understanding from that simple flat map of 2D chaos and extends it into the galaxy of higher dimensions. And it's not just some abstract proof. It gives scientists and mathematicians a concrete tool, a specific set of conditions to look for when they're hunting for stability in their own complex models, whether that's in physics, biology, or even engineering. It really pushes the boundaries of what we thought we could ever know. And that just leaves us with this one last tantalizing thought. This paper found a key to unlock infinite order in one very specific chaotic setup. It just makes you wonder, in all the other vast, unexplored landscapes of complex systems, from our weather to the stock market to the human brain, where else are infinite, hidden patterns just waiting for us to find them?